Welcome to this video on equivalent resistance of resistors connected in parallel with one another. Over here I have a configuration of 3 resistors connected in parallel with one another, connected in parallel with this battery of EMF1. Now parallel means that a certain circuit element has a connection to another with a junction in between the two. Now remember, a junction is a split in the wire. Now this is a little bit of a redundant drawing because I have this piece of wire and this piece of wire that aren't necessarily needed. I could directly attach that point to here and this point to here, but for the ease of showing it separately, we have it set up this way. But let's take a look at the conventional current direction, because ultimately we're going to use Kirchhoff's junction and loop rules to show how we can find an equivalent resistance of these 3 resistors together. When current passes this point, junction 1 we'll call it, the current will split into 2 portions. Some of it will go up this direction and some of it will go over here. Let's just focus on the bit that goes through the R1 branch. When it gets back to this junction over here, it cannot turn back upwards in this direction because that would be charges moving in the direction of high potential, which is not possible. So it would have to go in the direction of low potential. Remember, here we're dealing with conventional current. This current over here, of course, is going to split into R2 and then into R3, these particular branches, and then recombine at the node over here back together again. So if I asked you where is the current the greatest, hopefully you'd be able to say that the current is the greatest in this branch over here that the battery is in. And this branch, we are going to say that that current is going to be labeled I total. The current through R1 we will label I1, the current through R2, I2, and similarly I3 for the R3 branch. Now what I'm going to do here is write a junction rule, and I'm going to say that the total current is equal to I1 plus I2 plus I3 added together. What I can also show is that the potential difference across R1 or across R2 or across R3 are all going to be equal to the potential across E1. It's almost as though they're each independently connected to the battery. This is of course ignoring any resistance in the wires and resistance in the battery. So what I can show is that EMF1 is equal to the potential drop across resistor 1, across resistor 2, and across resistor 3. Now I do know that because we are considering these to be ohmic resistors, I can write the expression delta V is equal to I times R because the R will stay constant. I'm going to solve for I over here, so that's going to be equal to delta V over R. And now what I'm going to do is substitute that expression in for each of these I values over here so I can get them in terms of R instead of just I. So I'll write I total here. Well, actually, let's go ahead and do that for the total as well. We'll change that to delta V total over R total, or R equivalent, is equal to delta V1 over R1, delta V2 over R2, and delta V3 over R3. Now we see here that EMF1, or the delta V total, is the same across all of the resistors. So in other words, this delta V value can be factored out of every term, and what I'm left with is just 1. This leaves me with the expression 1 over R equivalent is equal to 1 over R1 plus 1 over R2 plus 1 over R3. If I want to isolate R equivalent on its own, I could write that as R equivalent is equal to 1 over R1 plus 1 over R2 plus 1 over R3 all to the negative first, or 1 over all of that. This is the equivalent resistance expression for resistors that are connected in parallel with one another. Be cautious, because if you've watched the capacitor multi-configuration videos, you know that this would be a similar expression, except R would be substituted with capacitance for the series configuration of capacitors. So whatever is the resistance configuration, the capacitance configuration is the opposite. So just be aware of that when you are looking at solving any problems. The last quick thing I want to look at in this video is if you had a situation where you had a combination of some resistance that's in parallel and some resistors that are in series with one another. Let's call this one R4. You would see here that R4 is going to have the total current running through it, whereas R1, R2, and R3 are going to have some split amount of that current passing through each of them in a subsequent time. Now, how do we decide, or how does the current decide, and we use air quotes there to say that, is how does the current decide to pass through this branch versus this branch versus this branch? Well, true to all kinds of energy configurations, the object of the movement here, of course, is the electron. It will always take the path of least resistance. So what we could think of is that if you pass through this R1 channel over here, the amount of resistance will determine how much current goes through. So the resistor with the lowest resistance will have the most current, and that will just naturally flow because of the potential drop needed to move across each of those subsequent resistors. A very interesting thing is that if you add another resistor here in parallel with the other ones, so if I put R4 here, it would actually change this substantially from what it was before. It's a very interesting thing, because essentially what you've done now is you've actually eliminated a total amount of resistance from the circuit. By adding an additional branch to the circuit, it's kind of like in the checkout in a store. If they open another checkout lane, that's reduced the total resistance to getting out of the store. So a way to think of it is the flow of traffic of people exiting the store will actually be a higher value. In other words, the total current will be a higher value because you have an additional lane that has been opened. You can prove that by putting in values here, and you can see that every time I add another resistance to this, the denominator of this inverse expression will get larger and larger, meaning that this value will get smaller and smaller. This is why adding too many devices to the same outlet can be extremely dangerous, because each one is connected independently to the power source. Adding too many of them is going to draw an insane amount of current, which will be a lot more energy. If you think of the video on energy and power, that's going to cause a lot of heat, and there you could start an electrical fire. Now, when you add resistors in series with one another, so adding a resistor right over here where I had it before, that will actually increase the total resistance, thereby dropping the total current. Keep in mind always that current and resistance are inversely proportional to one another. So adding a resistor 4 here would increase the total resistance, decrease the total current. Adding a resistor R4 over here would do the opposite. It would decrease the total resistance and increase the total current, which is the more dangerous situation.